Okay, so today we're going to start with diffusion model, but like any other time, we're first going to review the same thing and see that what we have learned so far. Okay, so we're going to just jump here. Up to this point, we learned about autoregressives. The idea of autoregressive is that data sequentially being generated, either text or pixels, sequential. It has some basically benefits, it has some pros and some cons. The pros is that if you have autoregressive, by default, you have exact likelihood. Why you have by default exact likelihood? Because when you try to calculate this term, these conditionals are known. If all of the conditionals are known, you have exact likelihood. If you don't have the conditional, that's the problem. That becomes a problem. You cannot do autoregressive basically. The cons of autoregressive is that they are pretty slow because it's sequential. Right, so they need certain basic optimization. Then we talked about flow models. And the idea in flow model was that, well, could we basically transform some distribution to another distribution, like some sort of like a transformation? Instead of X, could we use Z? So we sample from Z, but, and this should have some sort of like a deterministic deterministic and inverse relationship. The benefit of flow model is that if it's deterministic, that means from a latent variable, you can exactly go back to the data. The challenge here was that, well, the transformation is easy, but the distribution will change. And the distribution, basically, what we know about it is that there is this change of variable formula that basically what it says is that if you go from one distribution to the other one, the shape of the distribution also will change. And that is with respect to the function that you are basically using, the gradient of that function, and it has some sort of like inverse relationship. So that was the idea of flow models. Then after that, we talked about like a variational autoencoder, which the idea was that, well, that was the first type of latent models we talked about, which the idea was that we assume the data, any data fitting an image, has series of latent basically features. Image has a features like hair color, eye color, basically skin color, and so on. Again, it could be all of this. And could we come up with a way that we don't need to manually come up with those latents and let a model to learn all those latents? That was the idea of the VAE. And in VAE, one thing that we learned is that this problem, this likelihood, is not tractable. Why? Because in order to calculate this likelihood, you need to actually do this integration across all possible Z, which makes it intractable and hard to calculate. And then also we talked about this, that a really easy way, like not easy, the best way to solve VAE was, instead of trying to directly solve for that, we try to solve for the right-hand side using ELBO, evidence lower bound. The benefit of evidence lower bound was that because of the relationship, if we increase the right-hand side, automatically we'll increase the left-hand side. So that's how basically we try to solve it. But what also we saw in BAE was this term, this conditional term, this conditional term first doesn't exist. It's like a joint distribution, can be presented in two ways. Either Z becomes conditional on X or X becomes the conditional of basically on Z. Also, we basically talked about that, well, what we do something like an importance sampling. That means instead of using P of Z, we introduce Q, which becomes some like proposed distribution, which makes it easier to sample from. And that's basically becomes the easiest way to solve for a variational autoencoder. Then we talked about energy-based model. And in energy-based model, basically we said that, well, in what we saw previously in normalizing flow had lots of challenges. Why? Because there are lots of requirements, like on what types of model you can use, what types of network you can use. It's always like it's really limited. The idea was that, well, could we just use any function, any f of theta, instead of like similar to normalizing flow that's just limited? And we were like, okay, yes, we can do that, but The problem with is if we pick any function, that means any neural network, we need to ensure that the output of this neural network is always sum to one, is a valid distribution. Similar to what we know that's a softmax. Softmax is basically comes from this concept, right? So the idea is that you want, if I increase the chance of this image, the probability for other images should go down, right? So in order to be sure that your model has such a basic capability, you need to normalize it. And that's where this Z of theta comes, which becomes some normalization factor. One thing that we saw about this energy-based model is that there are ways that we can calculate that Z of theta, but itself is kind of become intractable. This integration becomes intractable and hard to solve for. That's why we basically talked about a score-based model, which we're going to go over soon. So if we go, let's first talk about GANs and then we go to a score-based model. So then there's another type of the generative model, which is GANs. And the idea of GANs was that all other models so far we have seen, they are kind of likelihood-based basically models. That means in order to solve it, you need to increase the likelihood, right? Could we come up with a model which is likelihood-free? It doesn't focus on the likelihood, and that's where the idea of GAN comes. GAN basically focuses on some sort of like a two-test statistics to compare probability of the data versus probability of the model generated by the model. So you want to basically ensure that these two are close to each other. So instead of doing likelihood, could we statistically test this? And we saw that, well, that statistically testing is also not that straightforward. So what GAN offered was, instead of we come up with that statistics, let's use another neural network, D, the discriminator. That is, his job is to basically look at these two and tells us that if one is valid, one is not valid. It's like it does, that's the same test for us. And that summarizes the basically GAN into basically min-max problem, which you are trying to maximize the likelihood of the original data and minimize the likelihood of the basically, we minimize with this with respect to the generator. So the loss function has two parts. It's kind of like a binary loss technically. So you have a increase in the likelihood of the original data, and you have your goal is that to minimize this part basically. Oh, sorry, this is one minus. So maximize this part becomes, that means for any data that generated by generator, the log of that, or basically the discriminator should give a really low probability. That's why you have one minus. If this is low, one minus basically becomes large. If the discriminator is not capable of separating the real data versus fake data, that becomes a challenge. What we saw about GAN is that GAN by default has lots of issues. One of those issues is that, well, it gets to the point that either even from the start, you could start in a really bad position, and then the generator cannot get any updates. That means the gradients that goes to the generator are really small, vanishing gradients. So the generator cannot generate anything, and discriminator always says that perfect. The other problem GAN had was the mode collapse, one of the famous problems it has. And mode collapse basically means that kind of memorizes. It's like if you have 5 images, 5 types of image that you can generate, it always basically generates one of those. It's just collapsed toward one certain basically type of image. And there are different ways that we saw that you can improve for GAN. So far, we have seen that, let's see. Yeah, so far we have seen like Kale divergence be really popular for comparing two distributions. But what we saw in GAN was that, well, there are alternatives to Kale divergence. One of them was Jensen-Shannon Kale divergence, which what it does simply ensures that this Kale is symmetric. So if in general you have Kale to be basically with, sorry, so if you have basically this log, like a P of X, Q of X, this, depending on which one we solve, Q for P, this always will be different. It's not symmetric. So in GAN, what we do, we basically have this term P of X plus Q of X divided by 2, which we call it an average basically distribution. And what we do, instead of comparing that, we basically compare the scale between the P average and the original P, 1/2 plus. And then we also compared the scale between Q and this basically average. And then we average that. So that becomes like a Shannon. The idea we want it to be symmetric. The next thing we talked about was that, well, Shannon also has its own challenges. The alternative basically you can use for GAN. One of them was F divergence. And the idea of F divergence was we could use any function as a divergence metric, but that function should have series of properties. The main property was that it should be lower semi-continuous. That means it shouldn't have any abrupt jump downward in this basically function. The other one was that, well, this at 1, the log of this always should be 0. Okay, so it's kind of like a valid basically divergence. And we also saw that the F divergence has some issues. And that's why we saw something was the Frenchen conjugate, which that means if you have any function, you can find a convex of that function. Okay, and instead of F, basically use that basically conjugate of F, which makes it easier to solve. Then the last divergence metric that we saw we can use was the Wasserstein or Earth mover distance, which the idea was that if I have two distribution, P and Q, like you have this and you have this, and you need to ensure that this will match to this one, how much effort do you need to go through to move this to here? That's basically Earth mover. And again, the reason it's called Earth is assumed that this is just pile of dirt. How much effort you need to do to move dirt from here to here? And basically that Wasserstein distance has two components. One component was about amount of information you're moving. The second basically component has the amount of effort. That means if I pick like I don't know, like a bucket, how many steps I need to go to empty that bucket? You combine those two, that becomes the amount of effort or the distance that you have. And the goal will be to basically minimize for that. And and that starts W GAN. And we saw that W GAN has much better properties in compared to GAN that use scale divergence because it doesn't suffer from that concept of it still suffers, but not that much. When the generator doesn't receive any basic gradient, because you always get some error that you can propagate through it. But if you just use numerical divergence, if the discriminator does a really good job, the generator doesn't receive any back propagation. So the gradient is almost goes towards 0. So that was that. Now, the next thing we talked about was score functions, which is a score space model. The idea here is that when we think about energy-based model, that z theta was not easy to calculate. So what we did, if we say that if we use these types of model, like a score-based, which instead of focusing on updating the model parameters, it focuses on updating the model with respect to something called basically gradient vector field. And gradient vector field basically tells you that if you have this, like you have a data and your data has series of modality, okay, like that means cat, dog, bird, like this is all your images. There are 3 modalities in your data. This gradient vector field tells you that if you're here, which direction you need to move in order to get to here, because you take the revision with respect, and you use that knowledge to update the model parameters. So your model parameters will be updated not with respect to how good is the image, but how to improve the data to go toward a correct modality. And what we saw that this gradient vector field itself is hard to find. So the idea of basically a score-based function was that could we estimate it? Could we have a neural network that gives us the same thing? And that's where this S theta comes. So S theta is the neural network that you have, which approximates that gradient vector field for you. It tells you that which direction you need to technically move. Instead of directly calculate it, you basically approximate it. One thing we saw about basically this energy-based score matching was after we simplified it, we reached to this term. The problem with this term was that you have basically a gradient and you have a Hessian. And this is kind of like expensive to calculate. Even if you replace this term, which is technically the neural network, you still need to do a gradient over that neural network. And when it's larger, that becomes expensive and becomes hard to calculate. So the idea was that, well, it's kind of like this approach is expensive. That's where the second types of basically score matching came. And the idea, like this next one. Noise perturbative score matching, the idea was that, well, instead of we trying to focus on the data and how to have build a better data, let's start basically focus on the concept of denoising. And the concept of denoising, which will be the focus of today's class, is, well, I have an image, I add noise to it, and my focus will be to learn how to remove that noise. Because, and if you think about this score field, tells you that if you're here and you're noise, which direction you need to go to get here. That's basically the idea, like just how to denoise an image to get to a good modality. Then we noticed that because after we simplify it, because the Q is simple Gaussian, the noise is simple Gaussian, this problem simply basically transfers to a score that your model generates. Basically, should be minus the basically the noise. So, and that's why it becomes the basically denoising problem, because you have a neural network that predicts how much noise is in this image, and you have the actual noise, and your goal is to minimize the distance between that. So by doing so, you come up with a model that, given an image at a certain time, it tells you that how much noise is currently in that image, and you just try to redact that noise and progressively basically improve it. So, so this had its own pros and cons. Like this. And that's why it basically starts today's topic, which is the diffusion models. Now, before we try to talk about diffusion model, actually, I have a couple of things to go over. So let's assume it's this really nice example for diffusion. So let's assume you have an image, and this is like an image that you have, and something like that. And the image is 3 channels here, RGB. Okay. And the original dimension pixel-wise is really large, doesn't matter. We just focus on 3 simple things. So let's say this is technically that's R, this is G, and this is B. And when you're looking at 1 pixel of the image, there is a R value, there is a G value, and there is a B value. So that's represent the image. Now, the idea that we have in the diffusion that we're going to go over is we will say that, okay, there is this like a simple Gaussian, like a generic Gaussian, that we assume this distribution. And what we want to do is that we want to randomly sample from this Gaussian. And when we say randomly sample from this Gaussian, that means if I pick a sample from here, if we have 3 channels, I get basically 3 values, 1 per channel as a simple, basically random number. Then what we will do here is that we pick this value, and this value, and add that noise to it. That does that vector. You just sum it. So what will happen here is that if this is your image, that becomes the next step, because now you added certain noise. And when you add noise, it just perturbs the image. So this maybe moves from here to here, this goes here, and this one maybe goes here. So that's the direction that we are basically moving. Then you repeat the process, and so on. So as you basically repeat the process, amount of noise increases and increases. And at final, you get to the image that it doesn't have any item in it, or basically any actual picture in it. It's just pure noise. Because you repeat this process, like you repeat infinite time. You just keep sampling and keep adding to the image. So the main part of the diffusion we will see today is actually just for destroying an image. You pick an image and you simply destroy it until you have just pure noise. Now, this overall, the first part of the diffusion is technically an encoder, similar to VAE. The main difference here is that in VAE, you learn the encoder. In diffusion, encoder is not learned. It's just a sample noise. There's no parameter, nothing to learn. We call it an encoder. It's just what basically process of adding noise to the previous data. So that means this is also by default is a Markovian, because every image depends on the previous one. So and just you simply keep adding noise to it. Now, the next part of the process, which is the decoder, is where actually we train a model in diffusion. It's basically you learn something. Now, the idea here is that let's say after a series of iteration, now we are here, here, and here. This is our data, basically. And this was some paths that we went. Now, the idea of the diffusion part is to if I'm here, how can I go all the way back and produce the same image? That's the diffusion, but that's basically what we are going to learn. And that's where you have a model with parameters. So let's see, there's a theta here, this model. Now that means here, how can I learn to follow this and get back to where I was? You know, that basically, that's the goal that we have. To how to basically be able to follow the noise and go back. Follow the noise and go back means so you're not technically randomly trying to denoise. You need to understand that how much noise I added and learn to find that noise and deduct that noise. So the path should be basically similar because you try to find how much noise I added. That timestamp, find that noise, redact that noise and go. By doing so, you basically get to this one and hopefully you have this image. So this is the whole general idea of diffusion. Now, why diffusions are basically become pretty strong? Because if you're able to break an image and then reconstruct it, you technically have learned a lot about that, basically the concept. But general diffusion models, it's called unconditional diffusion. We will see different types. They're only able to generate images, okay, like the same thing. And the image that's being generated, and we're going to watch a video on that, is not random. It's actually based on what you actually had during your training. So during training, like you can parallelize this part because for all the image that you have, you can just simply add enough noise that you get to this point. But what you want to do is that you need to know how much noise was added. Because during the diffusion part, when you go back at every time step, you have this model that predicts, okay, this much noise was added. You need to compare this with this much noise that was added here to see that if it's a valid detection. So if you repeat this process enough for enough images, you focus on training a model, a neural network, that's actually getting better of calculating this in compared to the true value. That becomes the idea. Now, so the general basically unconditional GANs, diffusions, they're still pretty strong. They're really good. They have challenges. Well, one of the main problems actually with diffusion model is that this is sequential. The diffusion part is sequential. You need to sequentially find the noise and reduct it. And there are some ways to optimize it, but that makes it slow. So diffusions are pretty slow. In compared to GAN, for example, GAN is like a one-shot generation for you. Now, there are different ways that the types of diffusion models that you see out there, like text to image and stuff like that, the way that these types of model can address something like that is during the training, you basically have this query that comes. So during the training, let's say you have an image and you have a description for the image. So this goes to some sort of like, let's say transformers, and it gives you some embedding. This embedding, which describes the text that belong to the image, we basically introduce it to the different type of GAN, again, diffusion that we see. This is called conditional GAN. So the generation part at every step during the diffusion will be with condition to the embedding that you're receiving. By doing so, when we diffuse, the model learns that, okay, if I want to diffuse, refers to this, like for example, I'm going to attend to this and understand that what does this image, this text basically tell me, describe this image. So when it tries to denoise, it also wants to be sure that it can generate something that's related to the text. And that's why in the conditional GAN now, you can generate images that, is just totally new, because you give some query to the model and say that generate this image for me. Now, how does that work? When you have this model learned, when you want to deploy it, user only provides a query. There is no image that user provides. User just says, I want an image of this. The first thing that you do is generate this one, pure noise, an image of pure noise. That image of pure noise and the query, embedding of the query goes to the diffusion part, and with basically gradually with respect to what was the query, it start denoising. But by denoising means that, well, for example, if it tries to create pixels, it says that, well, this part of the image is that this animal. So it tries to change the pixel somehow that gets closer to the user query as it basically goes through the process. Okay. Any question on that first?
So we're jointly learning both embeddings and
not necessarily. You could have the embedding is like a pre-trained model.
Okay.
That just embedding of text to basically text to content.
And the model will be able to generalize on embeddings it has not seen before.
So if you have a type of, like, it depends on how much you train, how much your models basically learn. But if your model during the training, it basically has learned how to correctly map the query to the images, during the generation, it will be able to produce. But if the model, for example, you ask the model to produce an animal, but your model doesn't actually understand the context. What's that animal? So, of course, the image won't. It should be something that it has seen during the training.
So, I ask. So during the training, all the pictures that we're using should be labeled, right?
So actually, that's a different type. So that's a really good one. So there's a different types of GAN. So there's diffusion, GAN. We will see there are different types. There's a type of diffusion which you actually have class label, and you also pass that to the model, like embed there. But during this version, you don't need to have necessary label, because this only, you have an image and description of the image. That description is the goal that you have, how to map a description to an image, But if you
every image in the
in your training
should have the
description.
Description, right?
Yes. Yeah. So if you are trying to create types of diffusion that maps query to image, yes, you need to have that
one. Like there is image and there is a text. So how does the theta is changed? Now the image has been converted to whole noise. So how that embedding has been related to that image, like to that noise.
That's your cost function. We will talk about that later. So you have certain types of cost function that validates whatever image being generated with respect to the query to see that if it's a good direction that you are going or not. So otherwise, this process is the same. You just, because you have an additional data that you're adding, is kind of like a guiding the model toward that concept. So if you also have a class label, the benefit of having class label is that if your data basically sits in a space like this, when you, and basically as part of the input, you embed a class label with an image, the model slowly learns that this image comes from this region, or this image comes from this region. So it's kind of like helps the model which direction it needs to move in order to denoise toward that concept. Right.
Okay, so in the encoder step, you are adding noise progressively and decoder does the reverse, right? So will the decoder have like access to how much noise was added during the encoder step so that it can do the same level of denoising to reach something?
So for comparison, yes, we have that because again, the encoder part is fixed, deterministic, like not deterministic in case of what it generates, but we know exactly what we are adding. There's some parameters that we'll basically use that we will see those.
In practical applications, I have particular interest in this encoder and then the diffusion model. Are they trained together or separately? Like encoding part comes first, then?
No, you don't. So you don't need to. So think about this. you're trying to generate image. You're not trying to encode.
Yes,
Encode is fixed.
yes.
Because otherwise, if they work together, it becomes a flavor like something like and like having two models that works at the same time.
Mhm.
You don't want to do that. You just want to be sure that you have a good encoder, gives you embedding,
Mhm.
and the generated image learns how to basically like encoding to create a content. You don't want to basically train both at the same time.
Do you think it will worsen the performance, or generally it doesn't happen
don't-
because it takes
Well-
too much computational resources?
To be honest, I'm not sure, but I don't believe having two models at the same time trained for embedding and generation will help with the performance gain. It's possible that, I don't know, maybe the encoder learns to maybe encode in a certain ways that the generator learns it better. That's possible, but I can answer that.
Where this embedding came to the game, kind of.
Different types of diffusion. That's the general diffusion. There's a basically this unconditional diffusion. There's a type called conditional diffusion, which you condition the diffusing of the noise based on some embedding of the query, some request that user has.
Some text or some that's been embedded, right?
Yeah.
Okay, but I have one question. You said conditional diffusion, right? And you mentioned also conditional GANs. What is this condition that they say? Is it a term that we add to the loss function at the end, something?
So imagine your goal is to generate this from Z1 through T. What is Z1 through T? We will see is these are Z1 through T, right? So here you will have another term, which is the query condition. So during the generation, your goal is to maximize this probability based on hiddens and some knowledge that you have basically provided. That becomes a conditional, right?
Yeah, because today I was reading a paper. They use it in conditional GANs for tabular data, and they were saying we use GANs, and again the same thing that you added that Q to the end.
Yeah, I mean, anytime it's conditional, you basically whatever you already have some like if you think about the GANs, right? They all always condition on something. So here, when you ask an additional condition, you just need to put it in the conditional probability or condition it based on that because you want to ensure that it generates with respect to that. Right. Question. All right. So what we want to do actually before
May I ask something?
yeah.
So after watching this visualization, my doubt was, so whatever the latent features we learned during the training, essentially our model is trying to
You're
push,
not learning latent features.
not exactly those characteristics, you could say, the image characteristics, like cat, dog, banana, or car, whatever.
No, you don't even learn that. What you're learning is denoising, a model that how to denoise, how to get rid of the noise, not what is a cat, what's a dog technically. That might be another type of conditional model. An unconditional version, you're not learning this. And as the video was explaining, it just, the image that it generates for you totally random based on just where is your, if you sampled from where, which cluster you're closer to.
See, those clusters, how does it know that this is the cluster? Because it learned that the X0 image, basically.
I mean, think about this. Over the time when you train this model learns to denoise. And when data goes, so this data being updated about how to get rid of certain noise, and automatically those data, they have some similarities, right? So that becomes that's
Clusters
basically the
that learn.
cluster that basically you're learning, right? But again, in the unconditional diffusion, we technically don't have that concept. Yes.
So how does the initial the red dots like in that pictures like it landed over there instead of like okay,
But just random, could be anywhere.
it could be anywhere.
Anywhere in the space possible. Yeah. It's just a random generation.
Like if my understanding is correct, this like consider this is like a cat cluster. This is a dog cluster. The training process is essentially telling that if there's random noise and if I'm asking for a cat, it should move towards the cat. Like
If you have a conditional diffusion, diffusion that's conditioned based on the class or some query,
Okay.
That condition guides the model toward which cluster it should go toward. Without that condition is just pure random.
Okay.
Or
The encoder has the clusters.
Encoder, so when you do conditional, that's correct. So you encode not the encoder. Your decoder, like the generator, learns how to map noise to a certain region of the space. You know, when it tries to update it, like I need to go this direction, the model, the decoder has learned that this direction goes to this animal, this direction goes to this animal. So it kind of knows that which direction there is conditioned based on the class label.
So you can go. So during the encoding, we keep adding noise, right? So let's say Q, we keep adding Q, and then after like say 2000 steps, we're done. So while decoding, why don't we think of it as whatever step we took at the, like let's say we are the first step of decoding, right? We've taken 1000 encoding steps. So the first step of decoding and the last step of encoding, they should be opposite.
Your goal is at optimal to be the opposite.
Yeah, so that could be the loss function we should be optimizing. That depends on that time step T. We take the opposite, like if
That's actually, we will see, that's one type of it's called kernel diffusion, which you're like, if I know how much noise I'm adding, I'm able to predict in one go to get here. But in the reverse process, you still need to gradually remove, because it's so easy to estimate and totally go to a wrong direction. So that's why in the diffusion part, you actually need to take steps and really small. You shouldn't take larger steps because you easily can. But in the forward, you can jump to the end in one go.
I agree that we should take small steps. But let's say we don't, even like, no, I say we should take small steps. But when encoding, let's say we are taking 1000 steps, and while decoding also, let's say we're taking 1000 steps, our function that we optimize, if it's based on divergence, right? If KL is asymmetric. So let's say if we have a symmetric strand divergence, we could literally do the opposite of what we did on the last step of encoding. And that is a function at time T.
But that's technically what we do. We try to do a divergence between this noise that we guess and this noise that was added.
Maybe I missed that.
Yeah, so that's technically what we denoising, because we want to know how much noise we added, how much noise we need to remove. So we will see that the prediction becomes actually how much noise the model think was added in the previous step. You kind of really reverse the process. All right.
Diffusion models are just memorizing path. And I think diffusion models, they won't perform well if our training data set, we don't have similar images or similar data sets. Because if, let's say we have 1000 images, it's different things like landscape, cars, routes, foods, it becomes random, extremely random. You give a noise, you just choose a path that's close to it and generates a pizza.
Yeah.
The next time it generates a mountain.
I mean, the unconditional diffusion, every time you ask a question, it gives you exactly something different, depending on where that randomness starts.
It's like you need to give enough samples of the same location so it can memorize it, basically.
But that doesn't answer what you said. The randomness of what it generates is not about how much data it has seen. If it's unconditional, it's just about where in this space that the random point is. And it goes to the closest, steepest, basically, hill. No, it's just because it wants to go up. It wants to increase the likelihood, right? And the vector field tells you that if you go this direction, this is the closest place you can go up. So it just goes up.
That vector field is just the history. Like it's seen it, like it's like I have 4 locations in my map, like location A, B, C. You put me somewhere, I'm gonna go just to those locations.
Okay, so how does that connect to your question? So let's say you have lots of image of, like you don't have enough images, but you have so many classes in the images, right? And you want to generate a data. You need to start somewhere randomly, right? If I start here, it will go there. Doesn't matter. Because that's the closest uphill that I can go. It's not about how much data of that you have seen. If I'm closer to this and this likelihood is highest, the gradient basically, the vector field tells you that this direction takes you to the highest basically density value. Right? If you have a lots of data now from this one specifically, so maybe the distribution around this become larger in compared to the other one. So maybe there's a chance now this becomes. So that can change the distribution of the data. That's correct. But having small amount of data with so many categories, that doesn't change the randomness of the generation. But also, just one comment about what we say is actually diffusion models. We will see the types of diffusion model. They're pretty strong. The quality of the images that they generate, like if you not go for unconditional, you go for conditional diffusion, they are really high quality. Yeah.
Do they have the capability to for the 3D also? 3D generation, 3-dimensional.
Yeah. I mean, yeah.
Space.
Well, 3-dimensional RGB is 3-dimensional, right?
XYZ, or not flat images, but rather.
I mean, I'm sure there are basically companies that do something like that.
I have a question. I wanted to ask, so is this form of a
Game
gradient
models.
ascent from,
Gradient descent.
okay, so when we do gradient ascent, let's say we take a data set like ImageNet, maybe so many classes, right? We take one class out of that. So all the images have, let's say all cats, let's say all cats. We give that, and when we are training this encoder decoder, we only train it on cats. Is there a way of actually making this completely supervised now, so that it's only going to give us cats in the gradient ascent?
Yeah, so that's what we're saying. So if you have, and so general diffusion doesn't have C class, doesn't have query text. Those are unconditional, just image to noise. Conditional, basically, or classified based diffusion have that and have that.
Any sort of changes makes it conditional then.
Yeah, so if you make it conditional based on something that you wanted to generate something, so it becomes conditional.
So how you said for this one that if a particular class has a lot of samples, then the what do you say? Like it can kind of overpower the other.
I mean, it all depends. It all depends on that vector field you have.
Yeah.
What we saw in the previous class, when you look at the vector field, you could have a modality that's really strong. So the vector, so the closer you are in this region, the gradients are smaller. If you have here, now the gradient to this might be much sharper because it tells you this is the closest path to go this direction, but the gradient to this one might not be that sharp. Right, so it's kind of like the direction it will pull you depends on that where is on the map that you are, the closest density region. Last question.
So we are always trying to make the image like go to whatever we've seen before, right? So if we in the query, if we ask like something like a red panda which doesn't even exist, and then how does it go to make an image that it was never seen before?
If the model doesn't understand the image, it's not able to generate what you think. It's like if you ask a question from GPT, if it doesn't know the concept, it generates you something, but wrong, right? So it will generate something still, but maybe not a red panda because the model doesn't understand. In the example that you saw in the video, the red panda, actually, if you watch the video later fully, is part of the data set. The difference is that every time this diffusion creates you an image, it's not copy of the original data. It's similar to that. So it goes to this region. Let's say this is red panda. It gives you one red panda. But that red panda, that's the thing about diffusion, is that you shouldn't be able to find that data anywhere on the internet. Because that's a unique data point being generated. So it doesn't exist. They become like a pure image. They don't exist online. Because it doesn't give you your training data, but it gives you something from here, depending on when it will stop. Okay, so now you all have a good idea about diffusion. So to summarize here, again, it's a probabilistic model, which it does some sort of like a nonlinear mapping. It's not deterministic because there's randomness in the noise that you add. So it's basically it's probabilistic. It's like a stochastic. And then it's similar to VAE. It has encoder, basically has decoder, but the encoder never learns anything just because it's just a straightforward noise that you add. And that basically becomes the idea. So you start from an image, you go to pure noise, and the process of the, like that's a forward diffusion process, and in the inverse process is where you basically try to remove that noise to basically generate the same data. Now, if you think about the encoder, decoder part, the encoder, you always have a forward conditional. In the encoder, Q is always Z, like the latent condition, like ZT condition on ZT minus 1. It's always your condition on the previous timestamp. In the basically reverse diffusion, you kind of like your reverse ZT minus 1 condition on ZT because you go backward in the process, right? So now the way that you could look at the distribution is that when you start with an image on the left, and image has this data distribution. So one thing about diffusion is that the data distribution should be continuous, but the original data should be continuous, but doesn't need to be Gaussian. So your original data distribution doesn't need to be Gaussian. It could be any continuous distribution, but as you go through the process and you keep perturbing this distribution until you get to a pure Gaussian noise, this perturbation, this basically Q that we will see, that's like also we call it like a kernel. That part, it's basically need to be Gaussian. So the original data doesn't need to be Gaussian, but these Qs, they need to be Gaussian. Okay, so except for the original data, the rest of it is technically a Gaussian manipulation, because you want to be able to add Gaussian to each other to basically combine Gaussian to create another Gaussian until you get to the pure Gaussian noise, okay, or Gaussian distribution. Okay. So now you can also again look at it this way. So as you go, data has a certain distribution. You basically start adding noise until you get to the last, which is the pure noise. And in the reverse process, remember in the previous class or last two class, we talked about something called Langevin dynamic, which is kind of like a sampling process. And Langevin dynamic basically says that if you have if I have a data starting point, and this data comes from some distribution, so basically this data has some value. What you want to do is that you want to go through a series of iteration to change this data. You can use it in a forward, which you actually add noise. You can use it in a reverse, which you subtract noise. But overall, in Langevin, you have for t from 1 to some number, and at every time, basically, you say the next data equal the previous data plus some deterministic value plus basically some stochastic noise. And there also could be some condition on if you accept that change. So in Langevin, you might actually have a condition that says that you basically check if this value is acceptable. If acceptable, you accept it as xt plus 1, then you go to the next time step. If not, you repeat it. So that's the idea of Langevin dynamic. So here in the reverse part of the diffusion, basically the sampling step happens via Langevin dynamic, but in a kind of like a reverse way. That means you subtract noise. One thing that's we will see is that in the Langevin, there is a part, basically some stochastic, some noise in the forward. In diffusion, even in the backward process, when you denoise, you still need to add some randomness to the denoising. That means if I go from ZT to ZT minus 1, the reality is that, well, we're not sure if this is that correct because we are using some model to take us there. So in order to be sure that the model is generalizing better and we're not basically exploiting one path to have some randomness, so we actually, even in the process path, we still add some amount of randomness to it because we want to be sure that this doesn't go in a wrong space and it's just more generalized. We will see that equation now. So in the forward process, the equation that you see here is Zi. It basically comes from these two terms, the square root of 1 minus beta times x, and this is Z1, sorry, like a first time that you're going to add noise to an image. X is the image that you have, okay? So you have an image, you basically multiply it by value, you add something to it. The beta is kind of like some hyperparameters as we saw that we have. It basically helps with the amount of noise that we want to add. The first term in the equation, a square root of 1 minus beta times x, that is a deterministic term. If you think about it, x is fixed, so you just add something to it. So that's kind of like a more deterministic. The second part is the stochastic. Why? Because epsilon is a random noise that you pick from a Gaussian. So the second part is basically the stochastic. The first part is deterministic. And now if you go to other time stamps, z2 through the end, then this value basically becomes like this. At first, it's only with respect to x, but it becomes with respect to previous time stamp, which becomes the Markovian part of it. So, and then again, this is a Gaussian term. Now, so these terms that you also basically see that the first term, which is the deterministic, it's kind of like a scaling factor that you multiplied by the x or zt minus 1 that you have, scale it. The second term, which is the stochastic term, is just add some Gaussian noise to what you have. Beta is something between 0 and 1. Z is the time stamp latent that you have, and epsilon is just simply a noise. Now, so let's see how we get from here, this term, to this distribution. Now, what we are saying here is that the second term, which is the stochastic term, which you multiply a square root of b, beta, by epsilon. What do we know about epsilon? Is a noise from a Gaussian. What's that Gaussian property? So is epsilon is coming from a Gaussian with mean 0 and a standard deviation I. Okay. So when you multiply this by a square root of b, what does it happen? Anyone tell us? How this becomes a Gaussian with mean 0 and variance beta?
Variance increase.
What's that?
Variance increases.
Change in distribution.
It's changing the normal distribution.
If you have a vector of numbers and you multiply it by a constant, what happens to the mean?
Stays the same.
Stays the same.
I mean,
Multiplied by the constant. What happens to the variance?
Where?
Multiplied by a square root of the value. So here, when you multiply the square root of beta by epsilon, the mean stays 0, correct? What happens to the variance? Multiplied by a square root of that square root of beta. So that's why it becomes a Gaussian with mean 0 variance beta. There's no square root anymore. That's the impact of the scaling, right? So that means that the second term that you have is always come from a Gaussian with mean 0 and the variance beta t. Now, it's important here to this beta t, because as you saw in the video, beta, it's gradually basically increasing it as you want to break the image. So at first, beta is small. As you go toward the end, beta becomes larger. And that has an impact when we change the beta. So if you look at the equation, the bottom equation, for example, as first, if beta is small, this is larger, the left side. So you have more, you preserve more of the x, or more of the current time step. The second term is small because beta was small. As time goes, the second term becomes the beta in the second, because the beta is larger, so the second term becomes more dominant. So you're adding more noise as basically time goes forward. So that's the idea, like incrementally basically increase the beta. So now this could also be a way of looking at it. So if you think about the green, that's the current z that you have, the distribution of the current z, and you have this noise, the blue, that basically you're bringing it. If you combine these two, basically it will produce something like a red, basically, because you have two Gaussian and now you are combining these two Gaussians. Now, when we combine these two Gaussians, the zt, which is the red, technically, comes from this equation, right? Square root of this times the previous z plus that stochastic term. That also gives us one thing. If you think about this value, that is coming from a Gaussian with this mean and this variance, right? So this term, the second term is the stochastic. That's where it defines the variance of the value to change. The first term, which is the deterministic, it acts as the mean of the distribution. So that means for every ZT, we know it comes from a Gaussian by default with mean square root of 1 minus beta t time the previous value and the variance of beta. Okay, so now we learn two things. So for the stochastic is always come from a Gaussian with that basically distribution. For this one, it always comes from a Gaussian with the following basically distribution, right? So now take a look at here. So in this image, you will start from top. So here on top you have X, and after 100 iteration, like we sampled 3 images. Okay, these are 3 different images, 3 different paths. So you sample this image, this image, this image, and over time, as Z increases, we add noise. What happens here is that because we are forcing this, by adding noise, we force this at the end to be a Gaussian with mean 0 standard deviation Y, they land in the same space at the end. Now, and that basically becomes like you have here, and you force all of this to go to a almost same, this is on 80, this is on 100. So if you go to 100, they overlap even more and more. So they become same distribution. So that's the process of forward that we do. We just break down the distribution, force all possible images to go to one distribution, like a simple Gaussian. Now, so that means, well, we can calculate this conditional. So if you think about this equation that you see, the image on the right, every image basically tells you that the conditional of next time step given the current time step. It's kind of like a Markovian, right? So if you have all of those conditional distributions, you can combine those, and you can basically have what is the general like a joint distribution for all the Z's, Z1 through T, given the starting point, right? And that simply comes from multiplication. So the reason the first term is out because these are all Z, we wanted to have a multiplication, so we brought the first term out of the equation. The first term is conditioned on the real image, and the rest of the term is a multiplication across slices across time, the latents that we have. Okay, any question on that? All right, so one other thing about diffusion is that the dimension of the data and Z, they should be the same. You cannot have a variational dimension. So if your image is, I don't know, like 256 by 256 by 256, you always go 256 by, like across. You cannot change the dimension. So now let's focus on the concept of the kernel, diffusion kernel. So let's start with one. Anyone here could tell us what's a kernel?
Something that takes the variable from a particular dimension to a higher dimension in space.
And what's a kernel in a layman term? Yeah, but what does it tell you? Kernels between 2 vectors, for example, what does it tell you?
X transpose dot product.
Take the dot products.
So what does it tell you?
Transformation.
How similar?
Similarity. Dot product is a similarity of 2 vectors. Kernel is a dot product, right? So if I have X, that it looks like this, and I have Y that looks like this, and I have X1, X2, X3, Y1, Y2, Y3. When you apply kernel, the idea is that let's say I need to take this image to a higher dimension, and basically, so let's say we do polynomial. So if I do a polynomial degree 2, basically, or polynomial here, this becomes 9 by 1, correct? From 3 by 1 becomes 9 by 1. And if you go polynomial over Y, you also get 9 by 1, correct? Every 2 variables basically multiply by each other to have a power of 2. So kernel basically tells you that if you do phi of X times phi of Y, the transpose of these 2, this multiplication, which the cost is 9, like a OD, right? So OD2, if D is 3, in order to calculate the dot product between these two, the cost will be OD2. Kernel tells you that you can calculate this using a kernel, basically that does this. That's polynomial kernel with cost OD, right? Instead of explicitly going to higher dimension, implicitly you go to higher dimension and you get the same similarity value between these two in a lower dimension that you would get in a higher dimension. Right, that's the idea of kernel. Now here in the diffusion, when we talk about kernels, what we are saying is that when we think about this sequence of adding, when you basically add values, the problem with the forward pass is that, well, you just need to sequentially add noises. But if we exactly know how much noise we are adding, if we know the process, could we come up with a kernel form of that? Instead of explicitly going through the steps, we could have a kernel that if I say, give me the noisy version at time t equal 100, it doesn't need to go sequentially go through that. It just produces the image at time 100. So that becomes the idea of the basically diffusion kernel. Now, you can look at it this way. So think about two time steps, Z1 and Z2. Z1 gets X as an input. Z2 gets Z1 as an input, right? Both of them, they have this equation. So if you replace Z1 within Z2 with the equation of Z1, right? You get to this term. Now, if you expand this term, you get to this term, the one on the bottom, correct? So you still, now if you think about this term on the bottom, Z2, the first term is the same deterministic term, right? The second term is going to be the stochastic. There is a noise, a scale, there is another noise. So if you combine those two, the last two terms. So the first one, you technically have 1 minus beta 1 times beta 1, right? Epsilon. Plus the second one is, beta 2 epsilon, correct? So if you combine these two, it will produce you the second term here, correct? So this term, if you multiply this by that, minus 1 will be exactly multiplication of these two plus that, right? So what do we see here? Well, we see that if we do Z2, there are two 1 minus beta. And then for this one also, we have 1 minus beta, 1 minus beta. Repeats 2 times. So the kernel trick here will be that 1 minus beta times 1 minus beta, we define it as alpha. So alpha at a given time equal multiplication of 1 minus beta, well, this I from 1 to t. That repeats in both sides, multiplication of 1 minus beta timestamp times the other one. So this term can be calculated here as dt. This is the kernel version. So what does this kernel version tell you? If I want to find noisy version of an image at a certain timestamp, I can calculate it just simply using the image. The input is image times alpha. And alpha is just a constant because you know the betas. You just calculate this constant and basically you use it over there. So that's the idea of diffusion. You don't need to sequentially go. You can basically predict what it will, basically deterministic, find what it will be, the noisy version of the image at a certain time. So technically in the diffusion, the first part is, you can have it for all images in one shot, depending on what's the beta and how many timestamp you want to go. For every image, you can predict, okay, this is going to be the noisy version at different timestamp. And also, if you think about it, from the pure noise perspective, like the forward basically noise, make the image noisy, the backward is the part that you're actually learning something. So in the learning part, maybe you don't need to do the forward. You just start with a simple noise, like a pure noise canvas, and you want to go backward. And we will see that we are using this to guide the model in the backward. Instead of calculating them, on the spot, we say that, okay, what was the image, like a noisy version of the image at this timestamp? And we pass it to this kernel, it gives us that, and we continue with that backward. So that's one way of optimizing for diffusion, is that we actually don't do the forward like that. We're actually using this kernel definition. Question on that?
So, in the earlier slide you mentioned we are actually using the Lagrangian dynamics to do the sampling, right? So we were adding the noise progressively so that there was some particular goal for that sampling, right? If we do this, we won't be able to, like, from time t to t+1, I won't be able to add noise that will help me reach my target. Like, I thought it would be the noise, the addition of noises, like, dynamically it will change based on some target.
Yeah.
So how will we?
We'll get to that part. Okay, just bear with me. We'll get to that part. Question. And that's a valid question. She's like, okay, if we proactively basically predict where it's going to be, how do we know the denoising part? Let us get to the that part that we go to denoising, and we will talk about that.
So for a particular point t, it depends on the previous statement.
Right.
We are using this formula to find how much noise we are adding.
No, so this formula doesn't tell us how much noise we are adding. It tells us at a certain time stamp, how does this image looks like after you added noise. Instead of explicitly add noise sequentially and go to that timestamp, you just have a formula that gives you that the result of that timestamp. So it's not about how much noise you're adding. Well, how much noise you're adding here is actually fixed. I wanted to talk about it in the next slide, but one thing that you see here as a change, epsilon is fixed, right? So epsilon is a fixed, basically, noise that you pick from a Gaussian. The difference here is that beta is changing, and beta you have a schedule for it. It's not like beta is random. You have a schedule that I want to increase my beta over 100 epochs, this in 100 steps in this form. You know, it's like you have that schedule. So you all at the beginning, you know how is your beta. That's why you can basically predict this ahead of time.
Basically, like giving us the output of, let's say, like 5 seconds of adding noise, something like that.
That's correct. Okay. Yeah. So not second, but like 5 steps, right? So that also means that this is valid. So this value, that multiplication basically, comes from a Gaussian with this mean and this standard, this variance basically. And this is, again, there is no square root because it's the same concept of scaling of scaling with the variance by certain multiplications, right? So that becomes the Gaussian. Now, so what's the benefit of this actually? What was the benefit of doing this thing? It has a closed form solution, right? So enforcing this Gaussian here, and also basically using this like a what's it called kernel version. Now you have a closed form solution for calculation, so which is pretty good. Every time you have a closed form solution, it's ideal scenario. So now this becomes idea of the kernel diffusion. So if you start from a certain x, you can predict where it will land without actually needing to go through the pass. Right, now that becomes the idea. So from here, you could go to anywhere here. The fluctuation that you see in the past, it's because you still have randomness epsilon. Every image, every step, you take an epsilon. So that's kind of like a random. So you have this stochastic nature by default. That's why you don't go exactly to same place.
Even in every time step, we also have different betas, right?
Yeah, no, I mean the beta is different, but yeah. So you do a sample Gaussian, noise, and that's also varies. But for the same image, if you repeat it, you don't go to same pass. You go different passes. So now we want to define the marginal distribution here. So a marginal distribution is focusing on Z. What is the marginal of the latent that we have? QZ. That's the idea. So you start from PX. This is the original data distribution. And as you go through it, and basically you add noise to the data, what you want to find is that can I basically answer what's the distribution of Q? Like Z here at a certain time step. You want to find that QZ. So the challenge here is that if you think about this equation, in order to find this marginal, you technically have two marginalization. You need to account for all possible Z. You need to account for all possible X. Because in order to answer what's the marginal at a certain level, you need to account, I could start here, I could start here, I could start here. And along the way, I could be anywhere in the space to get there. So this distribution comes from marginalization over possible X's and possible Z along the way, right? So which, if you think about it, well, it's not tractable itself. It's going to be really difficult. But if we now use the kernel version, like the kernel trick here, so the inner basically integration, this part, the QZ1 through given X, we technically don't need to calculate that because we have a kernel that tells us where exactly will be given X. Like we don't need to be conditioned on previous Z's. So that will change so that equation below, it's no longer dependent on Z because you can in one shot predict where you will be. So that will change to this. It becomes like one integration. This is the inner part. You just replace it with this term, QZT given X. And this was that kernel function that we saw. So this, did I write it? So that the QZT given X is that one. Because it was the kernel basically trick. So we don't need the inner integration anymore. So that's the kernel trick simplifies the problem. It still is going to be difficult because you still, you need to calculate across all possible X. So this is not going to be something that we can easily calculate. So now let's look at the conditional. So that was the marginal of Q. Now let's look at the conditional of Q. So conditional of Q is with respect to previous, like a conditional of Z with respect to previous time step, because it's kind of like is Markov, right? So so you have here QZ2, and the cyan line is conditional of Z2 with respect to Z3, and the orange line is Z3 with respect to Z2, and here it's Z3. So let's assume you have Z3, and you have this marginal of QZ2. So you can basically calculate this value, but what we do, we use Bayes theorem, basically. So in order to find the conditional, just all you need to do is use the Bayesian, because, and this is in a reverse scenario, if you think about it, because we say the conditional of, or the posterior of ZT minus 1 given ZT. That means we are doing a reverse. That could be calculated from this Bayesian, which on the denominator has the opposite direction of this posterior. So this likelihood is in a forward direction of adding noise, times basically the marginal of QZT minus 1. So in the image, the gray is the second term. The first term is the ZT given, so it's the orange line. And what we are finding is the cyan line. Okay, so this is the cyan line, this is the orange line, this is the gray line. And the denominator is just a normalization factor that we have over there. Yes.
So if you're using the kernel trick, we won't have ZT minus 1.
You can calculate it anytime.
But that could change, right? Depending on the epsilon, the noise, that could be different.
Oh, so I see what you're saying. So if you are saying that if I'm projecting, so that's actually well point. So if you go back here, that's why this trajectory is never the same. It's like every time you start from there, you actually go down a different trajectory.
Yeah, so I don't understand this, the Bayesian part, like why are we doing this? What are we getting?
So we want to find the posterior.
Like how the previous image changes the next one?
No, so posterior is focusing on this direction.
Decode.
How from here to go here? That posterior tells you that what's the probability of this given I was here? That's the posterior. That comes from two terms. On the denominator, you have this. What's the probability of here, given you was here? So reverse of that, right? Times, what's the likelihood of, basically, what's the prior of this?
We'll
That's
have to
Q.
use that to calculate it. It might,
Now we're just, bear with me. We're going to actually make this simpler. So we're not going to directly try to calculate all of these terms. So now the general problem is that, well, the term that the gray line itself is basically intractable. So we don't know this. We cannot calculate that because in order to calculate this, you need to assume every possible previous steps. So that becomes kind of like intractable. So and then if we think about it also is that the second term, this in the reverse, what it says is that this could be approximated for a small time step, not for jump, not for large jumps. So that's why in the diffusion process, we actually take time, like steps really small. In the forward process, you can just, take a larger steps, basically because you have also this diffusion kernel. In the backward, you actually need to ensure that the steps that you take are small enough that you can approximate it, and also you don't have much degree of freedom, like a degree of noise. So here, so this term here on the bottom, we can basically approximate this conditional diffusion. And if you wonder that where are this term coming from, this posterior basically tells you that this posterior comes from a Gaussian with this mean and this basically covariance, right? So if you have two Gaussians, one with mu1, one with mu2, covariance 1, covariance 2. If you want to combine these two, because mixture of two Gaussian becomes another Gaussian. So we know that for covariance, basically you get, I think it's like 1/2 covariance, covariance 1, covariance 2, inverse. If it's a 1/2 here, there, but probably yes. So that becomes the mixture of the covariances. Then if we look at the mean, technically this becomes the new mean, becomes, let's start them. The covariance times covariance of the first one, inverse mu1 plus covariance of second one, inverse mu2. We see if I'm not wrong. We have it maybe? I think that's it. So this is used to calculate these two terms because we are mixing two Gaussians. Let's see. There's no 1/2 here, so this is inverse. Yeah. That mixture, the covariance mixture for two, and this becomes the variance, the mean for the two. So this has basically combined this two term on the denominator together. There are two Gaussians. So if you mix those two, it will basically give you that. And this becomes like the approximation of this term using basically diffusion kernel. So instead of basically we need to calculate that, you always know that I can find this in the reverse using this equation. You know alphas, you know betas, and again alpha, we had it somewhere here, alpha times t is multiplication 1 minus beta I, correct? If you have the beta schedules, every term here can be calculated, right? All you need to do is that, but one thing that is important here is that, and that's why in the reverse diffusion, in the generator process, you cannot jump. You need to do sequentially because the steps should be small And also at every step, you need to know exactly the previous step because it's there. The ZT is there and the original data. Question on that? So that should be, if you think about it, that's the overall idea here. In diffusion, we force data from some continuous distribution to go to Gaussian and then to simple noise Gaussian and then reverse from that Gaussian to that complex distribution, right? Because we keep the Gaussians in between, that allows us to simply approximate and combine these Gaussians. If you had a different distribution for the kernels, then that becomes more challenging. All right, let's take a break here and then we continue. All right, so that basically what we just went over here. So let's now we want to basically focus on the backward process, this line-driven dynamic, which you start with the noise and you want to slowly, gradually remove the noise and hopefully get to a clean picture. Now, in the process of backward, if you think about it, let me go here. If you think about this one, this conditional, this is also part of the backward. That inner part, that mean value, so it's not that easy to calculate also. So here, basically in the process of backward using Langevin, what we are saying is that instead of we using that equation to find that mean, let's have a model. And this, when it says parameters by theta, that means you have a neural network here. You have a neural network that is going to predict that mean value for you. So instead of you actually calculating the mean, what you see in this equation, could we predict it using a model? So that is basically what we do here. So you sample from a pure noise and you, one at a time, you want to find this Q. So on here, basically what you see in this image, there are two terms. This Q conditional of ZT minus 1 to ZT. You can explicitly try to calculate that, that's difficult. Or you implicitly develop a model that gives you that. These two are the same. This is basically, the second one is what we do. We come up with a neural network, train it to predict that value for us. So that becomes a part of the generation. Now, if you think about the process, how we start. You start from a right corner, right? ZT, pure noise. Well, this is the distribution of pure noise, correct? So it's just ZT, the last term is a simple Gaussian, and that comes from this term because the mean is 0 technically, right? And the standard deviation is 1, or the variance is 1. Then when you move from this dimension to ZT minus 1 and so on, the difference here is that it still comes from a Gaussian. The first term on top, you see it's a Gaussian, but that term is technically this term. Instead of we generate this and this, basically, we are going to estimate it using models. Okay, so we do still the same thing. You're trying to one at a time denoise. In order to denoise, you need to have a mean and you need to have a variance because you do reverse of adding. So what we do here, we develop a model F, which is your neural network basically, which is going to predict that mean, that long term that you saw in that previous equation. And for the variance, we are actually forcing a fixed, because if you think about it, you have this sigma that you're adding, right? Like the variances. So you basically have this sigma t as the variance instead of this term, instead of the second term. Okay, so you basically define a variance per time step. So because of doing so, now these two terms are the same, right? So there's a Gaussian with this equation. Mean point, at the current time stamp minus the mean from the previous value. So what does this tell? Basically, this is kind of like a density value, right? So this density value tries to help basically predict the probability of this given that without explicitly finding the mean of this distribution and the standard deviation. You just predict it technically using a model. So if we now if you go basically also for the conditional, now we can find this is for the last part of the process. Means from here to here, the last time step. That's what you see on top is conditional of x, which means the real image given z1, given the last basically last hidden state. But one thing you will see here is that thetas. Every theta in this equation is with respect to the timestamp. That means these models are not the same, at least at the moment. For every timestamp, you have a model that predicts the mean. They have a different parameters. Okay, so it's not just one model that does all of it, at least not right now. Okay, we will talk about that. So you can now mix all of this. In the reverse process, if we want to answer one question, what is the probability of this, all of them together, the joint distribution, which is this term here. Condition on all models that you have, that you had one model per timestamp. When it says theta 1 through theta t, theta here stands for the models, right? What is this joint distribution? Condition over different fees that basically you have. And that's simply because this is all basically Markovian, becomes multiplication across conditionals, right? And we have three separate terms. The first term is PZT. Why it's outside? Because when you start in generation, this is pure noise. It's not conditioned on anything. The starting point. So PZT means the probability, which is a simple Gaussian. That's for the last step. Then this one, for the image, is also going to be separate from this ones. Because we just, for simplicity. So we wrote probability of the last timestamp, probability of the first timestamp, like the image, and multiplication of the rest of the things. All these conditionals. And all those conditionals, we saw above, the value will be generated using some neural network, some F, the mean of the basic Gaussian. So the goal basically is that, if you think about it, what am I trying to do? You want to maximize this, right? If I want to maximize this, during the upgrades that you go, the iteration, you update the thetas somehow that this become maximized. Right? So that becomes one idea of like when you do backpropagation to update parameters, the goal of the parameter update is to maximize the total joint distribution. Right? Does that make sense?
So the neural network is like one approach, you could even sample, right? To estimate.
Sample of what you mean?
From the Gaussian.
Yes, but that becomes kind of like more training and kind of like harder basically. Okay. So instead of actually doing it, that's approximate. And that's all of these techniques so far we have seen. Okay, square model, all of this, we try to avoid explicit calculation and do some sort of like model estimation.
Yeah. And so x0 means x, right? It's just like.
Yeah, sorry, this x0 and x should be the same. It means the data.
The data.
Sorry, x0 and x are the same thing, just means the data. Questions? So, right, so now how do we generate samples? These are the steps that you do. This is assuming that you have, during your training, and again, what is the training? You have lots of image. You basically bring your images and you convert them to these noises, like through the last. And then you pick a noise, the same noise, basically, and you're passing backward. During this, during the training, your goal is to update these phis, these parameters along the way, these models, by maximizing the joint or maximizing the overall likelihood of this image, the last image that you're generating. When it's done, when you have these thetas or phis along the way, then you start by sampling a simple noise, a canvas of noise, which similar to what you saw in the video, could be anywhere on the space. Then you start gradually deduct deduct noise from it. This basically what this tells you is that how to predict this the new value comes from this distribution as like a sample with this mean parameterized, sorry, with given this parameterized by that. This parameterized is related to the equation above. That basically is the parameterization. That means that probability comes from a Gaussian where mean is predicted by that model parameterized by phi or theta. All right, so that basically the phi that you see is related to the term f over there. So if you repeat this process enough, you should finally get to the last step. And this also comes from this distribution, right? So that becomes the final data that you have. Now, if that data is likely, if you compare it to the original data, it's like a likely data, that's good. If not, you basically want to do back propagation and update the parameters. No, sorry, this is for the generation. We already have done that. Now, let's see. So this is just a summary of what we saw before. So you have a forward pass encoder, you have a backward pass decoder. The only difference between these two is this term's kind of like this new term comes out and this reverses basically. This should be actually reversed. Should be x.
Given Z, yes.
Should be x0 given. Sorry, that should be reversed. All right. So now if you go here, how we actually can train that. Similar to any likelihood training model, what's the goal? Is that for images, you want that the final image that you are generating, this image, the log likelihood of this to be maximum. That means it's more probable. If you denoise an image that looks real, the probability of this should be large. So the log of this, basically, you do a log likelihood, right? So if you put that together, well, we say for one basically, actually L here is across all images. So sorry, I from 1 to L is all possible images that you have. Now, basically what you see here, our goal is to find parameters. How many parameters? Depending on how many timestamp you do in the diffusion. So T is the number of timestamp in a backward you go. Every timestamp has its own model. Every model has a parameter. So you have series of them. Your goal is that to overall argmax this. And what is the term inside? Log likelihood of one data. And you want the summation of that across all data. Why summation is IID because the data points are basically IID, so that becomes multiplication, becomes summation. Now, what we know is anytime we are trying to calculate basically this log likelihood, and it's kind of be like a challenging, we can do it another way similar to what you saw before, elbow. Like instead of trying to directly maximize for that, find the lower bound of it and maximize for the lower bound. So the elbow for this term comes from this. And one thing that we saw in elbow was we introduce a Q, like a proposed distribution, like it's kind of like important sampling. So these two technically cancel out. You see, you introduce one here, introduce one here. So this change this to an expectation. You pull this one out, change this to an expectation. Now this expectation, which becomes your elbow for diffusion, has two sampling. One sampling is for the starting data point. Where your starting data point comes from. You sample from proposed distribution. Because why? Because we don't know actually the distribution of real data. So we propose some distribution. The second sampling comes from the slices that you go. So you say these also come from some proposed distribution. So you try to maximize basically this. If you maximize this, automatically we know we maximize the left-hand side. Right? Similar to what you saw in VAE. All right? So just try to maximize the right-hand side.
Is there a scenario in this where we don't have to encode? We just start from noise. Is it possible? I'm asking a question.
So if you think about this, if you just simply from noise, the model doesn't know what to go back. Or where does it go? To noise.
Well, it has the image, it just we don't do the encoding process.
So you can basically, if you have an image, you need to create this first, right? Because what happens is, along the way when you add noise, this converts to totally this. But if you remove the noise, that should come out. That's the idea, that's your data.
Right.
If you don't have that, then if you just simple noise, you go, nothing comes out of it, or you just noise. So we noise it to denoise it. You need to,
That's necessary.
yeah, like this need to be noisy version of that data.
So it's not possible to learn that denoising without actually noising it.
Like if you don't have a data to learn, it just becomes noise minus noise, it goes to a noise.
Yeah, thank you. Thank you.
So now the other thing you will see here is that instead of trying to maximize in the alpha, we can basically try to do like a minimizing over the negative of the alpha. So that's something that happens in diffusion. So we basically doing a reversing that so this is larger than that. So negative of this becomes smaller than that, right? So we focus on the negative alpha. So you have this negative log value. You can expand it, and that will convert to this term. So this is becoming the loss function that we have. That negative log, the right-hand side, so it's a log of division, so separate those, so it becomes this term. So the first term, which is summation, so the summation is across the data points. So this first term is the nominator on here. That's the first term, okay? And because we already know the joint distribution comes from a Gaussian. That term that you see, we saw it here, right? Yeah, on top, right? So we say that this comes from a Gaussian for all data points, basically. I from 1 to all is the summation over all your data points. There is this term. What does this term tell you? If you think about it, similar to basically GAN, you had two terms. One term was over the real data. One term was over the generation. This is over the real data. You want, if I reverse and I get the real data, okay? If I reverse and I get the real data, this one, because this is the distribution over the last part. So this term is from here to here. From Z1, because if you see Z1 for any data point. So you predicting X from Z1 for all data points, the summation behind it for all data points. And what we are saying is that log of that. So you technically, you wanted this to be maximum, right? Because if the data that you generate is likely, the log of it goes toward 0. Right? If it's unlikely, that becomes negative. So we have this negative term behind it, so to make it positive for the funds that are basically having a large error. The second term on the other end comes for the denominator. If you think about the denominator, it's the conditional of all data points given the starting point, right? Sorry, conditional of all latents given the data. That's condition. And we already saw that we can calculate that using somewhere here. No, not this one. Where did we have that? Anyway, somewhere around this, that was this equation. So, anyways, so that basically says that the second term comes from this, which, if you think about it, it's a difference between mean and a variance. Sorry, and mean and the prediction. So you have a model at every time stamp. There's an F theta every time stamp. There's F theta. That F theta is responsible to predict what is the mean of distribution in order to go to the next time stamp. So you basically predict what was the mean. Now, the target is the mean, right? So this equation, basically, if you think about it, this is a closed form. We can calculate it. We had this equation. This was a closed form that given, I don't want to go slides back, but this was a closed form that for any time stamp, you can predict this mean given X and Z, right? So you have this target. This is an actual target that you have. You ask a model, predict it for me. Give me a mean. You compare those two. So the output of this model at this time stamp, an actual mean for that time stamp, you compare it. And you do this across all time stamps. That's why you have summation over timestamp to timestamp last one. That means from here all the way to here, you sum all these errors. Okay? This plus the error related to this part, the first term. Our goal is to basically to minimize this error. This is a negative, so this becomes a positive value. And this is a square, so it's always a positive error. So you have these two positive terms. Your goal is to minimize it. With respect to what? With respect to every model parameters along the way. When you do backpropagation, basically you want to update for every model how much contribute they had to the error and so on. Simple, basically, backpropagation. Does that make sense?
So the correction is based on the mean, not on the variance, right?
No, so it's because for the variance, if I go here, we had a term here, we keep the variance, look on the bottom, is deterministic.
Oh.
It's like a predetermined, sorry. So we don't need to predict it. We have it ahead of time, right? The mean is the one that we don't have. It's kind of like we calculate that every time. So our focus will be on learning that mean value and compare it with the actual mean that we have. And try to teach the model to reduce the gap between those two. Right. So that becomes the loss function. This is again, so far, this is for unconditional diffusion model. So that becomes the loss function. Now for the, if you're basically using a Gaussian distribution, this overall term becomes the difference between two means of two Gaussians, right? So that could simplify. Sorry, we're going to go to that one. So this is, let's simplify this. The first term is the target mean, which we just talked about it. The second term is the prediction. That's what your model gives. And the error becomes technically between those two. Now, why this works and why basically this helps, because the overall idea becomes along the way, we try to learn how much we added noise. And if you think about the way that we add noise, ZT always was something 1 minus beta or 1 times that previous value. And this we call it as the mean. And along the way, this mean expanded, become larger and larger. So that becomes the term. So the overall goal becomes focusing on the mean, because the variance was kind of like a predetermined values. Now, so now we can kind of do a reverse on this concept of the diffusion, the equation. So you have this Z formula. It's like a fixed. Remember, in the diffusion formula, you can predict for any Z given a starting point. Considering that, you should be able to also find X in the reverse equation, right? If you can find Z in this way, you should also be able to find X. So we also know that this conditional comes from a Gaussian with this mean and variance, basically a Gaussian with this mean and this variance. This is also going to be the what we want to predict. So this is the actual term. This is the model. Model wants to predict this value, the mean technically. So you're hoping to basically find that mean using a model. Now, all right. So now this comes around to like reparameterization, how we could basically reformat our decoder So what we want to do is think about this F. So you had this F, which you want to estimate the mean of this. And F is kind of like your model. One thing we also had was that we previously calculated this, right? That was the equation you saw in the previous slide. Now, what we want to do is that the noise, because if you think about it, how much noise was added? You need to kind of either keep track of it, or you need to actually basically calculate it. So now the idea will be that, could we estimate the noise directly? This is in the reparameterization. So remember the concept of reparameterization trick we saw in the VAE? We had this, during the back propagation, you had this stochastic node. We were like, okay, let's reparameterize it so it becomes more deterministic. Now here also, this noise is stochastic. Okay, it's a random noise. Could we just, instead of basically finding that noise directly, could we use another model to predict the noise? So that's where we introduce G. That's another neural network, for example, which is job is to predict the noise, estimated noise. So instead of having that stochastic noise, you just have a model that predicts, I think you had this much noise, right? So we reformulate the F. Wherever they had this epsilon, we replace it with another model. This becomes the reparameterization. So instead of, again, the focus is on the noise scale. Instead of we knowing the noise, the epsilon, let's have a model that its job is to, we're going to train it to predict that noise for us, to focus on learning that noise value. So now, and this is like why it's better, because, well, it's not a stochastic anymore. And it changes our problem, because now we don't need to focus on mean, predicting the mean. We actually changed, as part of reparameterization, we focus on predicting the noise. So the cost function, basically, the loss function becomes actual noise minus what was the noise model predicted. Before this reparameterization, the cost function was actual mean minus the mean that model predicted, right? So now we change this and say that instead of that, we're going to predict noise, how much noise was added. So you kind of make this more like deterministic. I know how much noise here, I'm going to deduct that much noise and continue. So that becomes your loss function, which is simpler, much simpler. Then if you go to, so this here, we're going to add a couple of parameters. It's just bear with me, we're going to break it down. So you have this Z, and Z had this epsilon. And we said this have this loss function, and loss function comes noise, actual noise that you added, minus the noise that your model predicted, right? This second formula. This expectation is just basically what it tells you, that a starting point should come from some Q, so data sample. T, the timestamp, should also be sample. So you don't need to go to across all timestamp, because now your focus is not gradual, is to do noise prediction. So you don't need to go through all T. You can sample T across time. See, that helps you now with the process of backward. I don't need to go through everything. I sample at a certain timestamp, see that how much noise was here, as the model predicted, and you see if it is good or not, instead of sequentially go back. So then the third one is the epsilon itself, because the epsilon, that in reality, the noise that you add is random. So you randomly pick a noise, right? Sample a noise, and you tell to the model, predict it. So the model basically predicts what was that random noise. So you have basically three sample, and a starting image, okay? It's like a starting image. Some random timestamp and some random noise. You combine the image with that noise. So inside this parameter, what do you see? That's the diffusion kernel. Given a starting point, I can predict at certain timestamp, how does it look based on the noise? So this tells you that one. I start with this image, and remember this alpha was multiplication 1 minus betas, and beta is fixed. You have it at beginning. So you predict my image at a certain random timestamp going to look like this. You pass that image to GT, your model, and you tell to the model, tell me at this timestamp how much noise was added. That's the inside the parenthesis. You deduct that from the actual noise that you sampled. So your model basically, think about it, what's happening here. You're asking a model that I sampled a noise. Using that noise, I perturbed an image from here to all the way here. So many times the same later. Then you're passing this image to a model G, and you tell to this model, what was the noise added? See? So that model is trained to predict that noise for you now. You combine that noise because you have the noise, you sampled it, compare them, and that becomes the idea of denoising. So your loss function becomes much easier and your training becomes much more efficient now. Because now you can sample, you don't need to sequential loss. The other thing here is that we have one parameter is lambda. That's kind of important. Why? Because, so what lambda basically says is that it's some hyperparameter, right? So lambda basically says, along the way when you add noise, this noise, they don't have same impact. So the noise that I added here at this time and the noise that has been added here, they shouldn't be treated the same. So lambda is some parameter which it's with respect to time also, with respect to alpha. You multiply it by this to account for this jump that you are doing. So you kind of know, even though I'm here, the noise that here has been added need to be scaled by a certain parameter. And that's what we have that lambda, to ensure that this sequence, we don't treat them all the same, because these noises should be different. Does that make sense?
Yeah. I just want to correct my understanding, please correct me. So initially we have different networks in between timestamps to predict the upcoming ones. Rather than having that many parameters to train, we replaced it with a simpler model, like lower number of parameters, which predicts the noise. And because we are predicting the noise, we are able to learn what type of variations we have and gone back to the same training data.
G doesn't necessarily mean simpler model. Doesn't mean simpler model, doesn't mean less number. G still is parameterized by T.
Yes.
So that means with respect to timestamp. Right? So in the general form, that G itself has a parameter phi of T. So you still have sequential, based on different timestamp, you have a different set of parameters.
Okay.
Right? So there are attempts or there are version of this that you only have one model to basically try to predict that for you. But in right now we are parameterizing by T at the time.
Okay, got it. So why are we coming? What's the simpler thing that happened because we replaced with G? Like, what is the advantage we got?
The advantage here is that you basically can. So in this version, you can sample any timestamp. You don't need to sequentially go. You can predict 10 timestamp from now how much noise was added and try to deduct that from the actual noise that you added. Right? Because we have this diffusion kernel that given an image and a certain basically noise, you can predict where this image will be 10 timestamp from now.
Oh.
So if I know I'm here after 10 timestamp, I pass that image, the noisy version of the image, to a model for a timestamp 10. That model has different parameters. It predicts how much noise was added. You deduct this noise from the noise that initially you sampled. So that makes it much easier than just simple denoising.
So this initial noise that we're sampling, that's pure noise. So
Pure noise.
So it's kind of telling us how far this intermediate noisy image is from pure noise.
No. So you deduct the noise. What this model predict is noise.
Yeah.
tells you that how much noise was here in this image.
Huh.
You deduct that noise from the noise that you sampled here. It's not about how pure is this noise. It's about how similar the prediction of noise that you did is from the noise that you actually added. Okay, this is an image.
This is an image.
This is a Gaussian.
Yeah.
You pick this point as a noise.
Okay.
You add it to this image. Then this becomes your new image.
Okay.
You pass this to a model. This G predict this point for you. That's the noise that you predicted. This is the gap between those two. You want to minimize it. You want to be able to predict how much noise was added. It's like a denoising basically function.
So now we can parallelly train this because it is not sequential anymore, like sample number of timestamps and.
Yeah, we'll get there. There are things on it, yes. So now this becomes a scale, like overall version. So sample, actual noise minus predicted noise, scale, average error. So this becomes your loss function. And again, that's one of the reasons that that this diffusion model is pretty strong, is that the training is not actually difficult, because it just becomes simply denoising of adding noise and predicting it, and basically making the model better at detecting that noise level. Now, this if you think about the training and inference overall, so you start on top. During the training, you have the data, you have a starting basically model, random, and the return, it will be updated parameters. You iterate like until convergence. You get some T becomes some uniform because you sample time based on what was the sample. Sorry, not based on, you sample, then you sample one noise. So you first detect time for right now, I want to train my model. So I pick an image, I randomly pick a time, says 100. So I said T is 100. I simply pick a noise, random noise. Then I update this, I pass that image, you remember the Gaussian, diffusion kernel? Pass the image and the noise and the time here. Then the model predicts how much noise was it. I deduct the noise and let this train back propagation. Your focus is to update 5 parameters of the model. When the training is done, you have 5s. You have all the parameters. You have a trained model. What would you do next? You go to a sampling. This is for generation. You start with a sample, simple ZT reverse, simple Gaussian. You start with pure noise. Then we use Langevin dynamic here. That's what you see in this for loop. Is Langevin dynamic. Langevin dynamic says that at every timestamp you want to denoise it. So, and this is not doing training. This is your training is done. It's for generation. So the next, like the previous timestamp come from this value. You sample some noise. You add it to it. Remember, as I said, and we saw this before, in Langevin dynamic, you have this epsilon that even though you're denoising, you will still add some noise to it. Why? Because you want the model to not go wrong direction. You add some uncertainty to backward process. Because otherwise, the model could go wrong direction. So you basically say that, okay, to be more generalized, I will add some noise to it to see that if you can basically go. So this process is Langevin dynamic. You repeat this for certain timestamp, depending on how many timestamp you had defined in your diffusion model. At the end, you get X. And X comes from this, the final X. Given Z1, that's how you basically calculate the final data. And that becomes your generated data point or image in this case. So again, you train a model, you find all the files. Start with a simple noise. Using Langevin dynamic, one step at a time, remove noise. This part is still sequential. You cannot jump ahead of time. The generation, during the training, we came up with a way to enhance the learning. So we could jump ahead of time. We sample time and we jump ahead of time and we mimic it. Because if you think about during training, we technically are not generating image. We learn how to denoise. So that's why you can sample during training. You don't need to go sequential. But during generation, when you want to generate actual data, you're not training, you need to go through every step sequentially. That's why it's still slow. Like GANs, you just pass, you get an output, one go. Diffusion is gradually basically adding basically things to it. Have you seen the latest GPT image, GPT-4? Have you passed image to it? How do you get the result back?
Sequences from left to right.
That's a diffusion, right? Basically, they first start with the empty canvas, and then slowly things comes up gradually. So what they have done basically is like they visualize it for you along the way. So you kind of like you're not just waiting for something, but you see it's pretty slow. So those type of model, they are pretty slow because they need to sequentially go through it. They also have some, I don't believe it's just one go. I think maybe they have some sort of like a layers that corrects it, which there's a types of, we will see in the next class, there are types of diffusion model, actually it says predictor corrector. So you have a prediction step, then you have another model that tells you that, no, this is not, doesn't look good, update it. Becomes predictor corrector, basically diffusion. Okay, so I think we can stop on this one. I would just quickly just talk about this image and then we stop here. In general, when you talk about diffusion model, there is a main architect of neural network that we use, and it's called UNet. So diffusion model by default are using something called UNet. Okay, now UNet is types of like simple kind of like a autoencoder look is it's like a CNN model UNet, which what it does basically extract features along the way. So you remember you need that GT, you need that basically model. So that predicts the noise. That's the unit. Now UNet, what we do, we add time representation to it. Why? Because if you think about this G, and when you sequentially generate image, you want the image to have some understanding of where in the process you are. Are you at timestamp? Like you have a model that by default, your model only does 100 timestamp to return an image. You want the model at every timestamp to know exactly where it is. Are you at timestamp 50? This is the quality and so on. So what we do, we simply have this time, and we pass this time to this fully connected, like a couple of layers fully connected neural network, converted to an embedding vector. We somehow should be same dimension that you can, actually it doesn't need to be same dimension because you concatenate. So you concat that embedding at every timestamp to the latent values that you have as you go. Just by doing so, you ensure the model to knows where it is. Why it's important? Because remember the G is based on T. The model need to know what is the time step in order to predict the noise. So you need to encode that concept of where you are in the process. So that's how we add the T in this equation to G. G, which is your model. You just encode the timestamp and concatenate it to the data that you have. Right. Any questions? Let me stop this.